I'm Tian from Shanghai Jiao University. I'm going to present our work, RAI2, Responsible Identity Audit Governing the Artificial Intelligence. This is a joint work with Shaofeng, Guoxing, Chen, Minhui, Haojin, and Zhen. Recently, we have witnessed great improvements of artificial intelligence. The AI model became a powerful tool for drawing, basic chat, and science problem solving. In principle, training a good AI model follows the development pipeline. Firstly, AI experts collect raw training data by web crawling or physical experiments. Then, the data are fed to the cluster for model training using multiple accelerators. Finally, after various model tests, the model is deployed on the cloud to provide the AI service through API interface. Obviously, model training is expensive because of a high accelerator price and power consumption, so the model is a valuable property and can be stolen by the adversary to build comparable AI service. To counter this, prior work has proposed various defensive solutions. In particular, existing solutions can be categorized into three types. Model watermarking refers to embed a watermark into models, but can degrade model utility. So model fingerprinting is proposed to mark the model by decision boundary fingerprints. Recently, Align work compares the model decision boundary by similarity checking. However, it has been pointed that the decision boundary can be reproduced, so it is not reliable for model identification. Moreover, prior work didn't consider the IP conflict, where the adversary can also claim the ownership using the same method, and they didn't consider data copyright protection. We argue that the training dataset is also a valuable property and should be copyrighted as long as the human efforts are involved. We show through an example on ChatGPT that training data is essential for model performance. ChatGPT is well known for solving simple mathematical questions, like the rabbit chicken problem. The problem is to determine the number of chicken and rabbits in a box given only number of legs and heads. From the left figure, we can see that the model gives a clear and correct solution using an equation system. But if we alter a little bit the problem, the model made a mistake and treated the wind like a rabbit legs. A possible reason is that the model only learned standard math problem but did not learn other problem variants during training. In general, training dataset is a valuable property because it decides the model's feature space and generalization. Therefore, both dataset and the model are valuable and their IP are worth protection. In this work, we categorize the IP threats from a more practical point of view. Suppose the victim company holds the proprietary dataset and the classification model. The adversary company wants to set up a comparable AI service by stealing the dataset and model through OS vulnerability or insider attack. This threat is real, and one recent example is the novel AI model leakage news spread on Twitter. Even worse, the deployed cloud server can stealthily modify the deployed model to frame the victim. The adversary capacity including mixing the stolen dataset with data of similar distribution, or change the model by post-training modification, like quantization, pruning, and fine-tuning. To deal with the copyright threat in the AI market, in this work, we aim to detect dataset and model copyright infringement by auditing their identity. Besides, we also aim to solve the fraudulent IP conflict. Inspired by the software copyright system, we consider to devise an AI copyright regulation system to allow dataset and model IP owner to register their property to a trusted third party. The trusted third party can then proceed digital forensics to discover copyright infringement through black box API query. Now we provide an overview of our framework. In general, our framework consists of registration phase and identity audit phase. In the registration phase, the owner can register his or her own IP to the trusted third party. The registered information includes dataset and model identity and time of the registration. With this information, the third party can audit the suspect's identity in the second phase. Specifically, the victim can request the trusted third party to proceed the identity audit of suspect's property, check whether two IDs are the same, and judge the real IP owners. We realize the whole process based on a commitment scheme. The registering can be formulated as the key generation. During generation, the victim generates the identity in form of a key and commits to the trusted third party. At the time of the audit process, the victim hands over the key to the trusted third party to unlock the registered information. Then, the third party estimates the similarity between the suspects and the victim's property. and judges the owner based on the similarity and registration order. So how to estimate the similarity between datasets or between models? In this work, we designed the dataset similarity estimation module and the model similarity estimation module. For the dataset, we define the similarity as the intersected proportion between the base dataset x1 and the target dataset x2. Our intuition is that the model output distribution becomes more centered as the similarity increases. This figure shows the confidence distribution on x2 of model trained on x1. We can see that as dataset similarity decreases, two datasets become less similar. The distribution becomes less centered. So our idea is to estimate the dataset similarity based on the output difference between the victim model and the adversary model with only black box query access. Firstly, the victim prepares identity information for registration, which includes a small sample estimation set and surrogate models trained on the dataset of S similarity with victim dataset. The surrogate model is to mimic a potential adversary model. To ensure efficiency, we choose finite candidate similarity values and prepare a lookup table. The lookup table records the expected output difference between the victim and the surrogate model for each candidate similarity. Then, in the audit process, the third party queries the suspect model to obtain real output difference and search the most similar output difference in the lookup table using t-test statistics, whose candidate value is the estimated dataset similarity. On the model side, we compare models based on the weights, as the weights are more explicit than the decision boundary and easier to compare. Because of multiple modifications, we propose to compare the weight difference in a unified projection space and define the model similarity between two models, as shown here. The H means the model projection vector, D is the distance metric in the projection space, and B is the upper distance bound between any two independently trained models, so that any two independent models have zero similarity. Inspired by the random projection, which uses the random transformation to project data into distance-preserving point clouds, we use random inputs to project model weights. The model output of Guoxing input depends on the inner weights, and our idea is to compare the distribution difference between two models' projection to measure weight changes. Specifically, to register model ID, the victim firstly obtains the model projection with the Guoxing input and trains an autoencoder to capture latent distribution of model projection. Then, the victim alters the model within a tiny range to determine the desired reconstruction error threshold. In the audit process, the trusted third-party queries the suspect model and estimates the model similarity with the victim's prepared autoencoder and threshold. As there are multiple modifications, the final judge follows the rules as shown here. Note that we use the static modification to represent the model quantization and pruning, because the weight update is not involved. With our proposed dataset and model estimation module, we can create each function in our framework and prove the following four security requirements. To prove, we use the assumption that any two independently created datasets and models have zero similarity, and leverage the binding and hiding property of a commitment scheme. For our experiment, we firstly evaluate the dataset similarity estimation and then the model similarity estimation. We begin with the experiment on these four visual and textual datasets and 6 model types. We randomly split the official training dataset into two disjoint subsets as the victims and the adversaries datasets. We apply common techniques to prevent overfittings and set the estimation set to 100 samples in our experiment, which is less than 1% of the whole dataset. The model accuracy on test data is summarized in the table. Our first observation is that the dataset similarity linearly correlated with the output distance for different model architectures. Here, the output distance is the average model output difference on the estimation set. We also notice that the curves are close to each other, especially when the similarity is close to 1. This verifies our intuition and guarantees the estimation accuracy of our lookup table-based solution. To quantify the accuracy of dataset similarity estimation, we propose the following metric called mu epsilon estimation accuracy, as defined here. For given estimation error, the smaller epsilon means more accurate estimation. Our lookup table-based results on tested model architecture are shown in the 3 figures below. Notice that on dataset of fewer classes like on CSIRO 10, the estimation is less accurate on the dataset of many causes like CIFAR 100 and Chinese ImageNet. We suspect the reason is that the model output differences are easier to be discriminated on data of numerous classes. We also investigate the sensitivity to adversary training setting. Given a dataset, the adversary can choose different learning rate and training epochs. In top 3 figures, we show the estimation accuracy curve on a different epoch scale, which is the ratio between the adversary training epoch and the victim training epoch. In the bottom 3 figure, we show the curve for different adversary learning rate, given that the victim learning rate is 0.1. We didn't choose larger learning rate as it will destabilize the training and degrade the model utility. From the results, we can conclude that the adversary training setting has few impact over the dataset similarity estimation accuracy. Our method can also be applied on text classification. We repeat the experiments on text classification dataset and BERT-based model, and obtain the similar results. We also conduct a case study using facial attribute dataset. In this case study, the 2 datasets are disjoint and are of a similar distribution. We unify the label from 2 datasets and use 2 recent model architecture of state-of-the-art performance. In our case study, the adversary knows the method but does not know the estimation set, so the adversary can adaptively modify the data, including Gaussian blurring and color jitter that randomly changes the brightness, contrast, saturation, and hue line image. The adversary can also train with fewer epochs that increase model output difference and estimation error. From the 3 figures, we show that the curves stay close to each other for different cases. We also compare our method with membership inference attack as a baseline for sublevel dataset similarity estimation. In addition to previous adaptive modification, the adversary datasets can also change. We investigate this case and compare with membership inference attack. The results are summarized in the 2 tables, where the bold number represents the better one. We can see that our solution obtains more accurate results for most cases. To evaluate the model similarity estimation, we adopted 3 visual datasets and set projection size to 1000 to achieve more accurate model modification charge. In our experiment, we used the KS test to determine the static modification and classify the RAI2 types based on the threshold. In this table, we see that if the adversary quantized or pruned the stolen model, the autoencoder's reconstruction error is close to that of the victim model, so the static modification can be accurately detected. To classify the RAI2 model modifications, for each dataset, we train 200 independent models using different but unknown random seeds for initialization. The threshold is the maximum reconstruction error among the equal number of fine-tuned models within 20 epochs. The table summarizes classification accuracy, false positive and false negative rates. Note that the most important result is the false negative rate because it measures the possibility that an adversary against the judgment. We found that the false negative rate is low and bounded by 4.5%, indicating that adversary has low chance to evade the detection. In summary, we devised the RAI2 that allows the owner to register their property and the trusted third party to jointly audit the dataset and model identity for copyright protection. In future work, a more comprehensive identity audit framework is needed for different cases. For example, it is still an open question to protect differentially private models and complicated AI generation system. Moreover, in the copyright field, legal efforts must be made for effective IP protection in AI industry. Thank you for listening. I'm happy to take questions.
Let's thank the author again by giving applause. Yeah. So